components of a refrigerating system, the four basic components of it. We have been discussing condensers and expansion valve. In the previous lecture, we have completed the condensers and its types, and we had started expansion devices. So we will continue with the expansion devices in this lecture. So what we had discussed, the capillary tube as a expansion device, and next we were discussing the thermostatic expansion valve. So this is what we were discussing last time. So in the thermostatic expansion valve, which is installed between the evaporator, which is between the evaporator and the condenser. Let me show you that. So this red one here is showing you the line coming from the condenser, and this is the expansion valve here in the center. This is the expansion valve in the center right here, the thermostatic expansion valve, and the evaporator is this one. This one is the evaporator here. This is the evaporator, and the thermostatic expansion valve is consisting of a bulb. So this the bulb right here, the bulb is containing another liquid, another refrigerant, which is not same as what is flowing inside your refrigeration system, but it's a different refrigerant here. And the green line here is showing the circuit of the thermostatic expansion valves refrigerant. Okay, so the way it works is that basically it is also controlling the amount of superheated vapor into the evaporator. So if there is a large amount of superheated vapor leaving the evaporator, so what it does that it will the heat of the superheated vapor will be transferred through the bulb into the refrigerant, which is in the thermostatic valve. So that refrigerant will boil up, and that vapor of that refrigerant will compress this blue diaphragm here. It will compress the blue diaphragm right here, this one, and as a result of that, it will compress this plate, and the spring will get compressed, and the opening between the condenser and the evaporator will open up, and more liquid will get into the evaporator. So if we get superheated steam, superheated vapor leaving the evaporator, then more heat will be transferred into the bulb, and the bulb will compress the diaphragm, and the diaphragm will compress the plate, and it will enlarge the opening between the evaporator and the condenser, and more refrigerant will enter into the evaporator. If suppose the reverse thing happens, that this evaporator was filled with the lot of liquid refrigerant, then at the end, at the outlet of the evaporator, will be getting saturated vapor, not superheated vapor. As a result, there will be less amount of heat transferred inside the bulb, and less amount of vapor of the thermostatic liquid will be created, and this diaphragm will be lifted up because under the pressure of the spring, and the plate will move up, and this plate will close. This plate will close the gateway between the condenser and the evaporator. So the amount of refrigerant going into the evaporator become less. So this is how it operates. So in this fashion, we can have more than one refrigerating capacity into the evaporator, or we can have different mass flow rate into the evaporator. So the same evaporator can be used for different loads. This is an advantage over the capillary tube, in which case we can only have one mass flow rate. We cannot change it. We can have only one refrigerating capacity. The cooling produced in a capillary tube type evaporator will be just one, but here we can have different loads from this from the same evaporator. So next I will show you the same video. We have seen it last time, just to give you a refresher on it. Okay, so here it comes. Thermostatic expansion valve is installed between the condenser outlet and the evaporator inlet, and it has a bulb which is installed at the outlet of the evaporator close to the inlet of the compressor. So it is basically controlling the superheat condition of the evaporator, refrigerant in the evaporator. So if the refrigerant which is leaving the evaporator is superheated, then that heat can be transferred to the bulb which has the thermostatic expansion valves liquid, and that will convert that liquid to the vapor, and that vapor will apply greater amount of pressure on the diaphragm. The diaphragm will be compressed, and it will open the gateway between the condenser and the evaporator, and more refrigerant liquid will enter into the evaporator. If the evaporator has a large amount of refrigerant liquid into it, then at the end of the evaporator it will be saturated vapor. The amount of heat in that saturated vapor will be less, so less heat will be transferred into the bulb. As a result of that, the thermostatic expansion valve liquid will not have that much vapor in it, so the pressure applied on the diaphragm will be less, and it will pull up the spring mechanism. As a result of that, the opening between the evaporator and the condenser will close, and less amount will enter into the evaporator. So this way we can control the mass flow rate into the evaporator, which is not possible in case of a capillary tube, and we can have different refrigerating capacity from the same evaporator. So this has the advantage over the capillary tube, over the capillary tube. So this is a good mechanism if we want to have different refrigerating capacity from the same refrigerating unit. So this can control the mass flow rate into the evaporator, and there is a very good mechanism here to do that. So I hope you understand. If there is any question regarding this one, you can ask during the question. So I have another video here that will explain you the structure of the thermostatic expansion valve. So the next video will show you the different components of the thermostatic expansion valve and how it is being manufactured, or what is the structure of it. So let's see that video here.
These, the thermal expansion valve by Danfoss. Coming up, where do we find them, what are they used for, and then we'll cut one open and discuss the internal components and how they work. If you want to get the most, expansion valves sit between the condenser and the evaporator in a refrigeration cycle. In this model, which is a T2 thermal expansion valve, we have the main body, which is made from brass. On the body, we have the refrigerant inlet at the bottom of the valve, then the refrigerant outlet at the side. And on the other side, we have a cap which can be removed. Under that cap is a screw which is used to manually adjust the superheat. We'll see how that works later on in this video. On the top, we have this large head called the power head. There's also a coil of very thin tubing known as the capillary tube, and there is a large bulb at the end of it known as the sensing bulb. These are all made from stainless steel. The coil is stretched out so that the bulb sits at the exit of the evaporator to sense the superheat. We have previously covered in great detail how thermal expansion valves and electronic expansion valves work, as well as the different types. What are expansion valves used for? Expansion valves control the flow of refrigerant into the evaporator in response to the cooling load. They measure the superheat at the outlet and react to this, increasing or decreasing the amount of refrigerant flowing into the evaporator to try and maintain a constant superheat. This also ensures that the refrigerant is boiling off, and it will leave the evaporator as a slightly superheated vapor and prevent liquid refrigerant entering the compressor. Liquids cannot be compressed, so if they enter the compressor, this can cause severe damage and even destroy it. The bulb is filled with a refrigerant which is kept completely separate to the refrigerant in the rest of the system. These two refrigerants never meet or mix, they are always separated. The superheat boils the refrigerant inside the bulb, and as it boils, it creates pressure. The pressure travels along the hollow capillary tube and into the power head. The power head controls the flow of refrigerant, and we'll see inside that later in this video. We place a removable cartridge inside the inlet of the expansion valve. This has an orifice which works with the valve to control the flow of refrigerant. There are different sized ones depending on the cooling capacity and the refrigerant being used. Okay, enough about that, let's cut it open and look inside. I'll just put the valve into a bench vise to keep it steady while I cut it open. Because of the delicate parts inside, I'm going to use a hacksaw to cut this one open. It does take a little longer, but the angle grinder could rip apart the internals and I want to be able to show you these parts. Okay, that's the first cut done. I'll just rotate that in the vise to cut the other side open. Again, I'm just going to use the hacksaw here to cut through it. That's pretty much cut now. I'll just use a chisel to snap the last little bit inside. And there we go. So let's have a closer look inside. So we have the main body which holds everything together. We have the refrigerant inlet coming in from the bottom of the main body in this vertical pipe, and then the refrigerant outlet on this horizontal pipe. So the refrigerant comes from the condenser and enters the valve body via the inlet. It enters as a high pressure, medium temperature saturated liquid. It then passes through the valve body, and when it leaves, it exits the valve through the outlet and will now be a low pressure, low temperature liquid vapor mixture. So what's causing the change in pressure, temperature, phase and also controlling the flow of refrigerant? Well, we can see this small pin here. This is connected to the diaphragm up in the power head. The diaphragm is a thin sheet of flexible metal. As the diaphragm moves up and down, it causes the pin to move up and down also. Underneath the diaphragm, we have a spring which is pushing up against the diaphragm. We can use this to adjust the superheat, and we'll look at that a bit later in this video. Above the diaphragm, we have this empty chamber which is connected to the capillary tube and then the sensing bulb. The chamber, the capillary tube and the bulb are all hollow. I'll just cut through the sensing bulb using an angle grinder to show you the inside. As you can see, it's just an empty cylinder which is usually filled with some refrigerant. The refrigerant in the bulb and capillary are completely separated from the main refrigerant which flows in the system. This isolated refrigerant only moves between the bulb, the capillary tube and the top of the diaphragm. The sensing bulb sits at the outlet of the evaporator. As the cooling load on the evaporator increases, the superheat increases at the evaporator outlet. Because the sensing bulb is in direct contact with the pipe at the evaporator outlet, the thermal energy transfers and causes the refrigerant inside the sensing bulb to expand and boil. Because the sensing bulb, capillary tube and the chamber are all hollow and are a sealed system, as the refrigerant expands and boils, it causes the pressure inside to increase. This pressure travels along the capillary tube and makes its way to the chamber above the diaphragm. As the pressure increases, it pushes down on the diaphragm and this pushes down on the pin. The pin controls how much refrigerant can flow, but to do that we need one more part. Inside the inlet of the valve we place an orifice assembly. Inside is a small strainer which protects the valve from blockages. Then there's a small orifice or hole which is blocked by a spring-loaded stopper. Our pin in the main valve pushes down on this stopper to open the valve. The further the stopper is pushed down, the more refrigerant can flow. As the cooling load increases on the evaporator, the superheat increases at the outlet. The sensing bulb at the outlet detects this and the refrigerant inside boils, causing an increase in pressure along the capillary tube. This pressure pushes the diaphragm down and that pushes the pin down, which opens the valve and lets more refrigerant flow. As more refrigerant flows, the superheat decreases and so the pressure in the sensing bulb and capillary tube decreases, which means there's less pressure pushing the diaphragm down. The spring then pushes the diaphragm back up, which causes the pin to move up, and as the pin rises, the spring-loaded stopper begins to close the orifice, which reduces the amount of refrigerant that can flow. This repeats constantly and stabilizes the valve to ensure the correct amount of refrigerant can flow. We mentioned earlier about adjusting the superheat control. Well, this plug on the side is threaded internally, and if we rotate this, we can move the slider up or down depending on which way you rotate it. As the slider moves up and down, it changes how much force the spring is applying to the underside of the diaphragm, which changes the sensitivity of the device and allows you to therefore tune the expansion valve and adjust the superheat. I just want to remind you that you can download the TXV Superheat Tuner app for free.
So that was all about the thermostatic expansion valve. I hope the videos are good enough to explain you its construction and its working principle. So the advantages of thermostatic expansion valve compared to the other types of expansion devices are that it provides excellent control of refrigerant capacity as the supply of refrigerant to the evaporator matches the demand. So we can have different load on the evaporator, and to match that, different refrigerant can be passed into the evaporator. So we can have different mass flow rate into the evaporators according to the need of our load. It ensures that the evaporator operates efficiently by preventing starving under high load condition. So it will help you not to let your evaporator starve. That is, it will never have low amount of refrigerant in it as compared to the load on top of it. So it protects the compressor from slugging by ensuring a minimum degree of superheat under all conditions of load. If properly selected. So if we have calibrated our thermostatic expansion valve correctly, then it will always have superheat condition at the outlet of the evaporator. So these are the advantages of thermostatic expansion valve. Next, we want to discuss the electronic expansion valve. The electronic expansion valve works on the same principle, that it also controls the superheat condition into the evaporator. So but the only difference is this one is the thermostatic is operated by a fluid, and in case of electronic expansion valve, it will be controlled electronically through a motor mechanism. So next I want to show you a video on that one. Electronic expansion valve, it uses a thermistor as a sensing element to vary the voltage to a heat motor operated valve. So this is the thermistor, liquid sensing thermistor at the end of the evaporator, which will sense the condition of the refrigerant leaving the evaporator, and it will send the information here into the applied voltage, and that voltage will change and vary and operate this electronic thermostatic motor, which is right around here. The thermistor is inserted into the vapor stream at the end of the evaporator. It has the following advantages: precise flow control over a wide range of capacity, rapid response to load changes, electrical connection between the components offer greater flexibility in system layout. The valve can close when the system shuts down, which eliminates the need for additional shut-off solenoid valve, which is required in case of a thermostatic expansion valve. So here, if power is off, then the valve will close automatic. The solenoid state control expansion valve is unique because refrigerant can flow in either direction through the valve by valve body, making it suitable for heat pump applications also. So this could be used in case of heat pump also, not just the refrigerator, but also can be used. The electronic expansion valve can be used for a heat pump also. So next I want to show you the video which will explain you the structure and the working principle of electronic expansion valve. So here it comes.
Mindset.com. In this video we're going to be learning all about the electronic expansion valve. We'll look at how they work, where to locate them, and why you should use them. Today's video is brought to you by our partners to precisely control the flow of refrigerant into the evaporator. You can find these on everything, including VRF units, inverter mini splits, heat pumps, chillers, AHU coils, etc. Now, we've previously covered how thermal expansion valves work. These are very common in refrigeration systems, but they are nowhere near as efficient or precise as an electronic expansion valve. If you haven't watched the video on how these work, then I highly recommend you do so. Links are in the video description below. Electronic expansion valves are an evolution on the thermal expansion valve. They are much more sophisticated and allow the refrigeration system to operate much more accurately and efficiently. You'll usually see the electronic expansion valves listed with the acronym of either EEV or an EXV. They both mean the same thing, it just varies by manufacturer. There are many benefits to using an electronic expansion valve, and I've listed some of the main points on screen now. The focus though is usually that by using an electronic expansion valve, you're going to reduce the energy consumption of the refrigeration system, as well as gaining much better performance. What do electronic expansion valves look like? There are many different designs for an electronic expansion valve, and I've put a few examples on screen now so you can see how their appearance varies. The difference in design depends on the type of system, the refrigerant used, and the pressure it's working with. As you can imagine, a small split AC unit isn't going to need the same valve as a high pressure industrial application, so the design is going to vary, although the basic working principle is essentially the same. Main parts of the electronic expansion valve. As we just saw, there are many different designs for electronic expansion valves, but we're going to focus on a simplified design to help build your base knowledge. This design uses a permanent magnet stepper motor. At the head of the valve, we have the stepper motor body, which contains the copper coils. These are used to generate an electromagnetic field, which will be used to control the valve's position. Sitting concentrically within the main body of the stepper motor is a permanent magnet. This permanent magnet is affected by the electromagnetic field of the coils, and the change in polarity of the electromagnetic field will cause the permanent magnet to rotate. Attached to the permanent magnet is a shaft. Now, some designs will use a gear assembly between the motor and the shaft, but as we're only looking at a simplified example, we're going to stick to a directly coupled shaft. On the shaft is a thread. This thread sits within a holder which is attached to the valve body. At the end of the shaft is a valve needle. Then we have the valve seat, which the needle moves into and out of to close and open the valve and control the flow of refrigerant. We'll also have some temperature and pressure sensors to take measurements of the refrigerant in order to calculate the superheat. These will be connected to the controller. The controller is then connected to the stepper motor and will tell it how much to open or close to maintain the correct superheat. So how does an electronic expansion valve work? If we have a look at a typical refrigeration system, you can see the main parts being the evaporator, the compressor, the condenser, and the expansion valve. The evaporator collects all the unwanted heat from the building and transfers this into the refrigerant, which causes the refrigerant to boil and evaporate. The compressor then sucks in this evaporated refrigerant, which is a low pressure, low temperature, and slightly superheated vapor. It then compresses this into a smaller volume, which causes it to be a high pressure, high temperature, superheated vapor. The refrigerant then moves to the condenser, where the unwanted heat is pulled out of the refrigerant and rejected into the atmosphere. This causes the refrigerant to condense into a liquid, so when it leaves the condenser, it will be a high pressure, medium temperature, saturated liquid. It then passes down into the expansion valve. The expansion valve causes a pressure difference between the condenser and the evaporator. It holds back the high pressure liquid refrigerant and decides how much to let through into the evaporator. As the high pressure liquid refrigerant bursts through the small gap between the valve seat and the needle, it drops in pressure. This will result in some of the refrigerant vaporizing, and the rest will continue through as a liquid. If you want to visualize this, it's similar to a water bottle spray nozzle. As you pull the trigger, the high pressure liquid is forced through a small orifice into a much lower pressure atmosphere, which causes the water to become part liquid and part vapor. This mixture of liquid vapor refrigerant is sprayed into the evaporator, where it will absorb heat from the air or water which surrounds the outside of the pipe, which forms the evaporator coil. In this case, we have a fan which is blowing air across the evaporator coil. As the refrigerant passes through the evaporator coil, it is exposed to thermal energy, which will cause it to undergo a complete phase change from a liquid to a saturated vapor, still at a low pressure and temperature. During this change, there will be little to no temperature change because of the latent heat, and instead it will increase in entropy and enthalpy. As thermal energy is still being applied to the vapor towards the exit of the evaporator, there is no liquid left over to change into a gas form, so the refrigerant will instead start to increase in temperature and become superheated. After the evaporator, we'll find a pressure transducer and a temperature sensor which constantly take measurements and sends this data to the controller. Not all electronic expansion valves will use this method. It really depends on the manufacturer and the system. Some simple ones will use a single thermistor at the evaporator outlet. Some will use two thermistors, one at the inlet and another one at the outlet, and then use a temperature differential as the superheat. But we're going to focus on the pressure and temperature method in this example, as it's a very reliable method and one you'll likely come across in the real world. The pressure is measured and converted by the controller, using stored data for the refrigerant being used in the system to find the saturation temperature. This is then compared to the actual temperature measurement. The difference between the two is the operating superheat. The controller then decides whether the expansion valve should open to let more refrigerant into the evaporator or close to reduce the amount entering. Once decided, the controller then sends electrical signals to the expansion valve stepper motor to energize the coils and create an electromagnetic field and vary its polarity. This forces the permanent magnet to rotate clockwise or counterclockwise depending on the polarity generated. Each time a signal is sent, the permanent magnet will rotate a fraction of a revolution to provide very accurate adjustments to the superheat. The shaft, which is connected to the permanent magnet, will also rotate, and as it does so, the threaded section inside the holder will cause the assembly to be pulled down. As the assembly is pulled down, it will cause the valve needle to reach the seat, reducing the gap between and restricting the flow of refrigerant. When the signal is sent to open the valve, the assembly will rotate in the opposite direction and the threaded section pulls the assembly up. This opens the valve and moves the needle away from the seat, allowing more refrigerant to flow. The controller is constantly taking pressure and temperature measurements and sending signals to adjust the valve position to suit the current load. When the cooling load increases, the refrigerant within the evaporator is going to boil off much quicker and the suction line pressure and temperature will increase. The expansion valve senses this and opens to allow more refrigerant in. When the cooling load decreases, the refrigerant will boil off more slowly and the suction line pressure and temperature decreases. The expansion valve will then begin to close to allow less refrigerant into the evaporator and maintain the correct superheat. Just before we go, I want to give one last shout out to our partners over at Danfoss and remind you to check out this video. Thank you very much for watching. I hope you've enjoyed this and it's helped you. If so, please don't forget to like, subscribe and share.
Okay, that was all about the electronic expansion valve. Next expansion valve is the float type expansion valve. So this float type expansion valve is normally used for large capacity system. It is not used in your regular domestic refrigerator or air conditioning, but it is used in industrial application for a chiller type of application. So it opens or closes depending upon the liquid level as sensed by a buoyant float. So it has a float like this one here. So it will open or close the inlet depending on the fluid level inside the tank. The movement of the float results in electric signal generated by an induction coil. The signal is amplified to switch the solenoid valve and can be adjusted for level and sensitivity. A throttle valve is fitted to provide the pressure reducing device. So it's basically functioning on a float valve, and it is maintaining the liquid level inside the tank or inside the drum. It always maintains a constant liquid level in the float chamber. Depending upon the location of the float chamber, a float type expansion valve can be either a low side float valve or a high side float valve. So we can install it on either side, low side pressure or high side pressure side. So low side float valve or high side float valve, either way it can be used, low side or high side pressure valve. Okay, so moving on. The float type expansion valve maintains the liquid at a constant level. So this is the float or the ball which will maintain the liquid level. Always established. This is the float or the ball which maintains the liquid level. Always establishes balanced condition of flow between the compressor and itself. Float valves and float switch solenoid combinations are used primarily in large installations. Regulate the flow to flooded evaporator in response to the level of evaporator. So in this one, next I want to show you its working principle and its mechanism. How does it works in the next video? So here is the video which will explain you its float type valves constructions and working principle of it. Okay.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at liquid level switches in industrial refrigeration systems to understand how they work and where we use them. It's time to make the switch to electronic liquid level switches. The LLS 4000 liquid level switch engineering, we looked at the main system components for single stage, two stage, as well as cascade systems. If you haven't watched that video already, then you can find links to that in the video description down below. In each of these systems, we saw a number of vessels which accumulate and release refrigerant to maintain the stable operation of the system. In these vessels, we have a mixture of liquid refrigerant as well as vapor refrigerant. The liquid level rises and falls during the operation of the system and the cooling demand experienced by the system. Now we don't want the liquid level to get too high or too low in the vessels. We need to maintain the level between our defined upper and lower limits in order for the system to operate smoothly. If we don't maintain this, then we're going to run into all sorts of problems. Now the vessels and pipes are made of metal, so we can't visually see inside them. We can install sight glasses and also liquid level gauges, but these will require constant manual readings. We need an accurate and autonomous way to sense if and when the liquid level is at the limits and automatically alarm the engineers to the issue. So for that we use digital liquid level switches, which look something like this. At the end of the unit we have a sensor. We'll look at how this part works in detail a little later in this video. But this part is going to be in contact with the refrigerant. Then we have a thread which will allow us to connect the device into the system and seal it in place. There is a hexagon head just above that which we will use to tighten the device into the fitting on our system. Then we have a heatsink. This is just going to dissipate the unwanted heat from the electronics. We want to remove this heat to ensure the electrical components last a long time and don't overheat. These fins just increase the surface area and allow us to dissipate more heat into the ambient air. Connected to this we have the electronic circuit board which has its protective casing on, and on the top of that we have the electrical connection which allows us to power the device as well as communicate electronically between the system controller and the device. Let's say for example we have this pump separator vessel in our ammonia refrigeration system. We want to ensure the liquid level of ammonia refrigerant stays between the upper and the lower limits. Mounted to the side of the vessel we have a column. We will probably find a sight glass built into this, and we might even have a liquid level gauge mounted to the column also. Both of these simply allow us to visually inspect the liquid level of refrigerant inside the vessel. On the column we have two threaded connectors which our liquid level switch will be screwed into. These are positioned between the upper and the lower limits of our vessel for the liquid level we want to maintain. So, as we can see, the bottom level switch is submerged in liquid refrigerant, while the top switch is within our vapor refrigerant region. That's what we want, because it means the liquid level is within our desired limits, so the system is in normal operation. The device is detecting the difference between liquid and gas, so when installing the device, we would need to pay attention to the potential for gas pockets. For example, if we install the device in a horizontal position, then as the liquid level rises and falls, any gas pockets will naturally dissipate. But if we install the device vertically, then there is a potential for gas to become trapped within the enclosure. This is going to obviously affect the reading of the sensor, and we won't get accurate results. We have previously covered purging ammonia refrigeration systems also. Links for that can be found in the video description down below. Coming back to the column installation, we could face the problem that the liquid level drops. In this case, the liquid level is going to come below a lower limit switch. The sensor will detect that phase change from a liquid to a vapor and will send a warning signal to the system controller. Additionally, we could face the issue of overfill, where the liquid becomes too high in the vessel. This means the liquid refrigerant will rise above the upper sensor. The sensor will also detect there has been a phase change from vapor to liquid and will again send a warning signal to the system controller. In either case, the switch activates an inbuilt relay which is used to sound an alarm and can be connected to the system PLC or programmable logic controller. The device uses a technology known as reflectometry, which emits a microwave at various frequencies from the sensor and into the fluid. These rebound back to the sensor with a pattern. Each fluid and the different states of the fluid create a different pattern. The pattern is the resonance frequency of the fluid, and each material has a different resonant frequency, so we therefore get different patterns. Liquid has a much lower frequency compared to gas, so we have these different plots. The resonant frequency is the frequency that causes the atoms of the material to vibrate. So, looking at a very simplified example, the sensor emits a microwave at a certain frequency over some atoms, which are bound together. This frequency has no effect on the atoms, and they do not vibrate. But as we vary the frequency through the spectrum, we find a frequency that causes the atoms to vibrate. As we continue through the frequency spectrum, the vibration stops. So by measuring these vibrations of atoms across the frequency spectrum, we can plot this pattern. A number of different refrigerants are tested and the results recorded by the manufacturer into the device. So once we configure the device and we specify which refrigerant our system is using, the device can correlate its measurements with the known properties, and thus we have our digital liquid level switch. This can then be used to detect a liquid or vapor and relay an alarm if the system goes into fault. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, LinkedIn, Instagram, as well as theengineeringmindset.com.
Okay, so now I hope that you understand how does a float type valve works or liquid level sensor works. So the next we want to discuss is the evaporator. That's all about the expansion valve that we had to discuss. Now let's discuss evaporators. As in the beginning of the previous lecture, last lecture, I had told you both condensers and evaporators are considered to be a heat exchanger. So the purpose of an evaporator is to receive low pressure, low temperature fluid from the expansion valve and to bring it to close thermal contact with the load, with the refrigerating load that we want to expel the heat from. The refrigerant takes up its latent heat from the load and leaves the evaporator as a dry gas. The function of the evaporator will be to cool the gas or the liquid or the product loads which is on the evaporator. We have based on the function of the evaporator, we can classify evaporator as evaporators which cools water or evaporators which cools air, or according to the manner in which liquid refrigerant is fed. So we can say that it is a direct expansion evaporator or flooded type evaporator. So what is a direct expansion evaporator? Direct expansion type evaporator, in most of the refrigerating evaporators, the refrigerant boils inside the tube and cools the fluid that passes over the outside of the tubes, for example air, water or brine. So evaporators that boil refrigerant in the tubes are often called the direct expansion evaporators. This is the evaporators that you are familiar with, which is used in your refrigerator or in your split AC air conditioner. So the refrigerant is inside the tube and it is expanding inside the tube, going from liquid to gas, inside the pipe, inside the tube. Okay, and the medium which it cools, that is outside, that is the air that it is cooling down. So air is the one which is which is losing its heat to the evaporator, liquid evaporator refrigerant. And as opposed to that, the flooded type, the refrigerant vaporizes on the outside of the tube. So inside of the tube is another medium. It could be water, it could be brine solution, it could be anything, but the tube or the pipe contains the other one and the refrigerant is outside of it. The refrigerant vaporizes in flooded type, the refrigerant vaporizes on the outside of the tube, which are submerged in the liquid refrigerant within a closed shell. The fluid to be cooled flows through the tubes, usually used with rotary screw or centrifugal compressor to cool water or brine. So this is an example you are looking at. So in this one, the shell contains the this is the shell which is containing the refrigerant, and these pipes or these tubes have the, so this is the shell and this is the tube which has the water or brine solution in it. So the refrigerant liquid will be fed from the bottom and it will cool down the liquid in the pipe and it will boil and evaporate and it will go out from suction line, outlet line from the top. While the liquid will be in from one side and it will pass, so it's like a two pass, fluid will be coming in from this way and it will go out from the other way. These are the head that lets the control the fluid that you want to cool down. So there is some other examples of this kind that I want to show you, that the examples of the evaporators, direct expansion evaporators. Remember, in direct expansion evaporator, the refrigerant is inside the tube. So in all three of these are the pipes contains the refrigerant, and the fluids that we want to cool down, that will be inside the tank, so that they will absorb, like brine solution, like in the ice plant. we have the evaporator inside the tank and the brine solution on the top. So similar kind of arrangement in case of ice plant. So in this case, the refrigerant is inside these tubes, these copper tubes that you can see, and the brine solution or the water or the liquid that we want to cool down will be inside the tank. Whereas in the flooded type evaporator, the refrigerant is in the shell, in the tank, and the liquid that we want to cool down, it is inside the pipe. So I hope you understand these two different types of evaporator. Now I want to discuss a little bit more on other components that may be used in a refrigeration system, in a refrigerating circuit. So moving on, this diagram, if you look at it, it has your famous 4 components. That this is the compressor here. This is the compressor right here. This is the condenser, and this is the evaporator, condenser and evaporator right here. Okay, so these are the 4 component and expansion valve. This is the expansion valve. This one is the expansion valve. Okay, this one is the expansion valve. So these are the 4 components there, but beside that we have a filter dryer on the condenser side, we have a filter dryer on the evaporator side just before the compressor. So the function of this filter dryer is to make sure that only liquid can pass into the expansion valve, into this expansion valve, and gas should be stopped right here in the liquid receiver. So liquid will be passing on. This pipe is inside the liquid, so it will only take the liquid, or if there is any gas, it will, or vapor, it will just drain it back here, and only liquid will pass it on. The side glass is used to show that this is only the liquid which is going into the expansion valve, and also it can be used in certain cases to control the amount of refrigerant that you want to go inside the evaporator. But as you can look at the expansion valve, this is like a thermostatic expansion valve or a electronic expansion valve, so you don't need to control your mass flow through the side glass. But if it has a capillary tube here, then yes, this side glass can also be used to control the mass, because there is a level in it which will show the liquid level of the refrigerant which is going into the capillary tube. So you can control with the help of this. You can also see that if your refrigerant is enough into the circuit or it is low, so you can charge more refrigerant into your refrigerating circuit. So after this, it comes into the evaporator. After the evaporator, it goes into the accumulator. Okay, this is the accumulator for superheat condition, or if there is some liquid coming, then this filter dryer will further expand the liquid before it goes to the compressor, so that no liquid should go into the compressor. And after the compressor, we have an oil separator. Normally the oil is inside here into the compressor, which is lubricating the piston and the cylinder surfaces, and the suction valve and the discharge valve. But in some cases, there will be always some amount of lubricant which will leave the compressor. Normally only refrigerant is supposed to leave the compressor and go into the condenser, but in very little amount of a very small amount of oil can also leave the compressor. The lubricating oil can also leave the condenser. So to separate that so that it doesn't go into a condenser, because it works as an insulator, we have an oil separator. So it will separate that oil which is coming with the refrigerant. So the refrigerant will pass from here into the condenser, and the oil will be trapped here, which will be fed back into the compressor again. So these are some extra components which is sometimes used into the refrigerating circuit. So I hope this explains you everything about the components and and their working principle of a refrigerator or air conditioner system, or any refrigerating system, any HVAC system. These are most common components. There are other components that are used, but these are the most common ones. So I thank you once again, and I hope you will go over all these all this information that we have presented here, and if you have any questions you can prepare it and we'll take care of it during our live session. Thank you very much once again.